You know, seeing the behind the scenes of stunts is pretty cool. All the safety measures and neat tricks like hiding the stunt person's face with smart camera movements. However, today, I'm here to get theoretical. I want to see if by the laws of physics would these stunts be possible without all the bells and whistles that make stunts safe. So where better to start than Bollywood? What? We can't play the intro for copyright? Whatever. Hello, Internet. Welcome to Riff Theory, the show that only exists for a physics project. RRR is the pinnacle of Bollywood to me. It is pure action-packed, overly dramatic, emotional cinema. It's everything Bollywood, and it's amazing. Plus, among stunts, I'd rather do a more niche movie. The movie is set in 1920s India, where two men, Bhim and Ram, come together to fight the British Empire. That's all I'll tell you about the movie, as I recommend you watch. The stunt I'm analyzing is when Bhim and Ram first meet to save a boy from an exploding train. In this scene, Bhim on a motorcycle and Ram on a horse tie a rope to themselves so that they can launch themselves off the side of a bridge connected by a rope, and swing themselves to catch the boy and throw him to safety, as well as make sure they don't burn into flames. How they did it was much of the scene was visual effects, and for the stunts, first, only some of the shots were they actually using a horse and motorcycle. For example, the turn into the bridge, the horse was instead a cart on rails, and the motorcycle was attached to a steel beam that rotates around an axis. The rail makes it more stable, as the force that would send them flying is inertia, Newton's first law, and the force preventing that is centripetal force, aka the strong friction between the rails and the cart, which, fun fact, is why train wheels are slanted, so when they turn, the radius of one wheel becomes larger, allowing it to cover more distance. The tension in the very strong steel instead of the weaker friction with the ground is how the motorcycle is more stable on the turn. The actors then have harnesses on strung from cranes in order to exaggerate how far they fly when they make the jump, and to give them more control over how they move while still having the rope they use in the actual scene. The tension forces from multiple directions with the multiple ropes attached to the harness prevent the force of gravity and jumping off the bridge from spinning the actor around due to the air resistance over the irregular surface of a person. The strings also are able to pull the actors farther in the direction they want, and the harness applies this force over a larger area, preventing injury by distributing the weight, aka the force of gravity, over multiple sources of tension rather than just one. It's also very impressive, they still had the actual rope as they calculated the length for the height when they used the actual bridge instead of the flat mock-up. Now that we know how the actual stunt was done, would this feat be possible for Bhim and Ram to perform during the time period? Now, this is where the theorizing comes and me messing up math and physics, so I hope my friend who is a physics major doesn't get mad. Oh, and I guess my physics teacher too. I'll just be going over the physics of the jump rather than the train exploding, and this will be super simplified to the level of physics I can comprehend. First, let's address if the rope will break. The most tension force in the rope will be when Ram, Bhim, and the boy are at the bottom of the swing, as gravity is pulling straight down on the rope, and the force of gravity, aka weight, is at its most. Using good old Newton's second law, net force aka total force equals mass times acceleration, we can find the force on the rope. Since acceleration is gravity being 9.81 meters per second squared, we just have to find the masses of the people. The actors for Bhim and Ram have their masses on line, 78 and 75 kilograms. However, we'll have to find the boy's mass on our own. To get the boy's height, we use this shot with good old pixel measurements. First, by looking up the height of a Victorian lamp, we get the length of each pixel to measure the boy's height. Looking up the average weight of boys in India in the current day and taking off a bit for the time period, we can assume the boy is 50 kilograms, which is pretty heavy for an 8-year-old. Plugging those numbers into the equation, the tension in the rope is around 1,991.43 newtons. Again, using pixel measurements for the thickness of the rope of 16 millimeters, and assuming it's made of hemp, we can look up the strength of the rope, which is 15,000 newtons, so this rope will not break. Good for Bhim and Ram. The fall, however, would cause some issues as the rope is static and doesn't stretch like a bungee cord to spread the force out. The force is not enough to injure the spine, but due to inertia being objects in motion want to stay in motion, all their insides would still be moving when they are stopped by the rope. This would cause injury as all their insides would be moving now into the rope, and their head, which is loose, would jerk back as well, which is called whiplash, and may cause head and neck injury. So that's not the greatest, but they would still be fine. But would Bhim make it to the jump in the first place? We went over centripetal force and how it's tension for a rope, but for a motorcycle, it's friction. This equals to the coefficient of kinetic friction, aka how tough it is to move on a surface, multiplied by normal force, which due to Newton's third law, everything has an equal and opposite reaction, would be the weight from gravity. The motorcycle looks like the Triumph Model H, which is 80 kilograms. Assuming the fuel tank is full, that will add another 5 kilograms, making a total of 163 kilograms with Beam's weight of 78 kilograms. The road looks like concrete, which has a coefficient with rubber of 0.6, and with the acceleration of gravity, the force of friction is 97.8 newtons. Now, since the force against the friction is our good friend inertia, we just need to find the force of the motorcycle, so we need acceleration. And to get that, we need initial and final velocity. The final is easy. Using pixel measurements with the motorcycle as reference, we can get d divided by t equals 7.5 meters per second. The motorcycle, however, does not start at rest, as it is kept in place as beam is on the gas. The velocity of the wheel is then needed, which is equal to 2 times pi times radius times frequency. I counted that the wheel spins 8 times in a second for frequency, and I looked up the radius to be 13 inches, giving us 16.6 meters per second. The time in between is 16 seconds, giving us an acceleration of negative 0.7 meters per second squared from VF equals VI plus AT. So he actually slows down before the turn. Multiplying that, we get the force of 92.91 newtons, which is low enough that Beam will not be crashing into Ram. So since Beam and Ram are mostly good, let's check on the boy, which means we need the velocity of their swinging like Tarzan. To get velocity, we need the length of the rope. I decided to calculate this by seeing how far they would fly off the bridge when they jump. For Ram, it's simple, since his horse stops before he jumps, so his velocity is only created from the force of his jump. Using pixel measurements to calculate his jump using d divided by t and a little bit of trigonometry for the horizontal velocity of 1.2 meters per second, which his jump is pretty impressive. Beam, however, jumps while his motorcycle is moving, therefore would fly farther. Assuming speed is constant for the turn, we use the final velocity we found earlier and added together, the total is 8 meters per second. Now using the formula distance equals velocity times time plus acceleration times time squared, we can get how far they fall and subtract how high they jumped. Then finding the horizontal and using the Pythagorean theorem, Beam's side is 20 meters and Ram's is 14.6 meters, which is a slight issue seeing the bridge is 15 meters tall, but let's ignore that part that makes this entire situation impossible. The centripetal force at the bottom of the swing is equal to tension plus weight, and we have both, and we can set the equation to equal mass times velocity squared divided by radius, and get velocity for Beam of 22.15 meters per second. Now we go in reverse order to find the force on the boy's arm, which is 147.6 newtons, which unfortunately is in the range to dislocate someone's shoulder. Whoopsie. However, this pales in comparison of the real danger, the throw. Getting the velocity of Ram with the boy's weight of 14.76 meters per second, and using some trig with the angle of the rope the boy is thrown and reaching a max height after 2 seconds, we find that the boy is falling at a distance of, drumroll please, 6.8 meters. This is bad news, as falls from this height, which is over 2 stories, is going to at least cause broken bones in the legs and at worst, death. So, in classic theory fashion, when the heroes try to save somebody, it results in an even worse outcome. But hey, that's just a theory. A Riff theory. And cut. Just want to end this video to say thank you, MatPat, for inspiring the little theorist in me and inspiring this entire video that's taken me so long to make.